So I'm going to talk about the momentum operator, the energy operator, the kinetic energy operator, Schrödinger's equation, and put Schrödinger's equation into the 3D context. But first, as we recall from the previous video, psi in free space is x of t equals to e to the I kx minus omega t. And as we recall for the photoelectric effect, E equals h times f. And note that f, the frequency, can be written as omega over 2 pi. Thus, E equals to h omega over 2 pi. Thus, it could be written into E equals h bar omega. From Du Bois, lambda equals h over p, and that means p equals h over lambda. If we multiply this by 2 pi over 2 pi, we get h over 2 pi times 2 pi over lambda. 2 pi over lambda is k. 2 pi over lambda is k, the wave number. So p equals h bar. P equals to h bar k. We have these two relationships, which is really important. And let's start for the momentum operator. So the momentum operator first, where do we start? If we take the derivative, the partial derivative with respect to x, and multiply it by h bar over I, where we take the derivative of the psi of x of t, we get a peculiar relationship. First, h bar over I, and I'm taking the partial derivative of x psi of t. This equals to h bar, and we're taking the partial derivative of this, right? Of that. So, what will this get us? This will get us ik psi of x to t. The reason why we have this constant up in front, h bar over I, is because it cancels out, as you can see. And what will we end up here? Equals to h bar k psi of x t. And this, you may realize that this is literally just p psi of x t. So we define h bar I x to be the momentum operator, and we call it p hat. So p hat psi of x t equals to p psi of x t. Okay, let's turn to the energy operator. Still with psi of x of t equals to e to the I kx minus omega t. This time we need a different constant. This time we're taking the partial derivative with respect to t. So I times h bar, partial derivative with respect to t, psi of x t. And the reason why we have I times h bar, is because we need to cancel out the front of the derivative and get h bar times omega, which is energy. So this equals to I h bar multiplied by I omega. Notice how the i's cancel out and they eventually equate to 1. And that multiplied by psi x of t. This will get us I bar part of t, psi of x of t equals to h bar omega psi of xt. What will this get us? This will get us E psi of xt. Thus, we define, this is the energy operator. It's defined to be I h bar partial derivative of t, which is also defined to be E hat. Moving on, the kinetic energy operator. So from E equals 1/2 NV squared, we can rewrite this into P squared over 2M. Great. And what do we have here? Basically, we can have, let's define this as E, kinetic energy. Call it E1, so we can differentiate from the other one. Psi x of t equals to P squared over 2M psi x of t. What would this get us? Notice that we have, notice that this portion, we can rewrite into this. P over 2M P psi of x of t. And note that we could write this in terms of the momentum operator. Basically, this part is equivalent to P hat psi of x of t. And we could make this an operator because it's also we could also do this. H bar I with respect to x, bar with respect to x, t as p to m. We can because this p could also be applied to all of this. This could also be written as p hat, so 1 over 2m h bar over I partial derivative of x, h bar over I partial derivative of x applied to psi of x of t. This will get us negative h bar squared divided by 2m partial derivative, second partial derivative. And we got this relationship. So Schrödinger equation, going to denote as SE. So as you can see here from classical mechanics, we know that the net energy equals to kinetic energy KE plus PE, potential energy. Let's set PE as a function of V x of t. What is our net energy? Our net energy is h bar omega. Kinetic energy is P squared over 2m, and we have our potential energy. So h bar omega, we have the operators for them. So what we have here is E hat equals P hat squared 2m plus V of x of t. And notice how I got this part. This part is from up here. This thing is also equivalent to P hat squared 2m. over 2m. So this is our operator in operator form. And if we apply psi of x of t to both sides, that means psi of x of t to p hat squared 2m psi of x of t plus v of x of t psi of x of t. And we could rewrite this operator as, we could rewrite all of these operators, these two, into this one will be I h bar partial derivative t psi of x of t equals to negative h bar squared over 2m second partial derivative to x squared x of t plus v of x of t times psi of x of t. This is, note that this is just a function. This is a function, not an operator. And we could factor out psi of x of t, h bar, right here. We could factor out plus v of x of t. We could factor out psi of x of t, and we define this as the Hamiltonian operator. This is the Hamiltonian. So Schrödinger's equation in operator form, can be written as E hat psi of x of t equals to the Hamiltonian times applied to the psi function psi of x of t, and there we go. There is Schrödinger's equation with all its glory. Now let's apply this to 3 dimensions. So in 3 dimensions, let's define R as x hat, y hat. Actually, not in unit vector form, could be just any basis. X, y, z. And our wave function in 3 dimensions is r of t equal to e to the I k subscript x times x plus k subscript y times y plus k subscript z minus omega t. How do we get here? Well, this thing can also be written as k dot r minus omega t. 3 dimensions. SE 3. Okay. Notice that only the momentum portion or the kinetic energy portion up here, there's three parts to it. So we could generalize this. What this essentially means is that, remember how we derived the momentum operator? We have h bar over I, partial derivative of x, derivative of x. And when we apply that to the wave function, while right now we're doing R, we get ikx omega t, kx times psi r of t. That means this part will equal to h bar kx, k subscript x, partial derivative x, kx, psi of rt. That means that's the momentum in the x direction, psi of r of t. Well, we could repeat this process and get that py r of t and get pz r of t, psi r of t. And what is the total? We can add them up. Essentially, remember the del operator being this. When we apply h bar over I times the gradient operator applied to psi of rt, we can get the sum of these three. Sorry, just common habit when I just do this. I keep making the x in order. We get this. That means the momentum, well, recalling from here, this thing will literally just turn into h bar I dot h bar I times the operator, because we're summing them up and there's three dimensions to consider, and the del operator will cover that for us. This will get us to negative h bar squared 2m applied by the Laplacian. Thus, the Hamiltonian here, now the Schrödinger equation, we can still write it as this way. The only difference here is that our Hamiltonian operator now equals to negative h bar squared 2m Laplacian plus VRT. Notice the V also needs to be in 3 dimensions. And that is the kind of derivation of Schrödinger's equation and the kinetic energy operator, and momentum operator.